Hello everyone, in today's lecture we are going to talk about polynomial. So, before we introduce what is polynomial, the first concept I'm going to introduce is power function. What is a power function? If a function can be represented in the form of fx equals to s to the p power, we call this is a power function. So, this is the base, where the base is a variable and then the exponent is a number, p. So for example, fx equals to x to the 7th, this is a power function. Fx equals to q to the 8th, this is another power function. Q is our variable. Or, oh sorry, this should be q. Or g of t equals to t to the 5th power. This is also a power function. Now, I am going to show you in a decimal what does a power function look like. So here, for our first function, I'm going to type in y equals to x squared. It's going to be a parabola, which is our quadratic function. And then what if y equals to x to the 4th power? Also, it's really like a parabola open up, similar to a quadratic function. And then let's say y equals to x to the 6th power, the green line. Still, it's really similar to a quadratic function. So now let's go some bigger power, such as power to the 14th power. The purple line represents that function. Also, they look like what? Parabola, right? So, what do they have in common? Well, in this function, what they have in common is, for the long run behavior, we call it long run behavior. That means the function all look like a U shape. So that means this is a x goes to infinity to the right. So if x goes to the right, y goes up, right? If y goes up, so that means the function goes to infinity. So we can summarize that. As x goes to the right, y goes up. So s to the right is infinity and y goes up is infinity. And now look at the other direction. If x goes to the left, y also goes up, right? So to the left, that means it's negative infinity. So that is, as x goes to the left, which is negative infinity, y goes up, which is a positive infinity. Okay, so these are when fx equals to s to the power p, when p is what? 2, 4, 6, 14, they are even number. When p is even. Okay, so now let's take a look what if p is a odd number. What do they look like? Y equals to s to the cube. It's like a curve. And then what if y s to the 7th? This is an odd number. And then y equals to s to the 11th. Also, the blue line looks like a curve. So what about y equals to x to the 19th? So what do they have all in common? They all look like this shape, right? They are quite similar to here, when the power is a odd number. So when y equals to s to the p, when p is a odd number, we have what? as x goes to the right, the function goes up, right? So I have as s goes to a positive infinity, which is to the right, y goes up, which is a positive infinity. But as s goes to the left, which is a negative infinity, y goes down. If you look at the graph, so if y goes down, that means y goes to a negative infinity. So okay, let's compare to when the power is even and odd. So when the power is an even number, the function look like a U shape, right? They're similar. They're long-run behavior. Long-run behavior means when s goes to infinity, either negative infinity or positive infinity, the function will goes up. But if p is an odd number, as s goes to positive infinity, y goes to positive infinity. But if x goes to negative infinity, which is a left side, y goes down, this is a negative infinity. So this is the long-run behavior of a function. So now let's discuss what is a polynomial. So polynomial is a function can be written as fx equals to a to the s to the n plus a n minus 1 s to the n minus 1 plus a to the s cubed plus a to the second. If a function look like this is called polynomial, and each ai, which is here, a sub I, we call it coefficients. A sub I are all real numbers. It can be positive or negative or zero. Can be a whole number, a decimal, or fractions. So what is terms? So term of the polynomial is any piece of the sum that is any of ai s to the I. So each individual term is a transform power function. So in here, how many terms we have? I'm going to use a red pen to circle the term. So this is one term, this is another term, this is a turn, this is a turn, this is turn, this also a turn. So the next concept is the degree of a polynomial. So the degree of a polynomial is the highest power of the variable that occurs in the polynomial. So in this case, our degree is what? What is the highest term? Is our n, right? In here, that is the highest term, n. Okay. And then the next concept is leading term. So leading term is the term containing the highest power of the variable. Highest power of the variable. So the term with the highest degree, basically. So now if you take a look, which one is the highest term, contains the highest degree, which is a sub n to the x to the n power. So this is our leading term. So if this is our leading term, so a sub n is the coefficient in the leading term, we call it as what? We can call this as a leading coefficient. Okay, so now let's take a look. The polynomial, I'll give you some identifiers to some degree. I'm give you some examples so that you can identify which one is the degree, the leading term, the leading coefficient of this polynomial. So I want you to find the degree, leading term, and the leading coefficient. Of the polynomial. So for example, I have fx equals to 3 plus 2x squared minus x to the cube. So remember our definition of degree is what? The degree is the highest power of the variable occurs in the polynomial. What's the highest degree occurs? S to the third power, right? So third is the highest power, so the degree of the polynomial is 3. So what about the leading term? The leading term is the term containing the highest power, which is here. Don't forget the negative sign because that also considered in the term. So it would be negative x to the third power. And then the leading coefficient is what? Negative 4, because our leading term is negative 4 to the s cubed. So our leading coefficient should be negative 4. Again, let me show you another example. G of t equals to 5t to the 5th minus 2t to the 3rd plus 7t. Okay, what's the degree of this polynomial? Well, the degree should be the highest power that occurs, right? Which is in this case is the 5th power. So the degree of the polynomial is 5. So what about the leading term? The leading term is the term containing the highest power. This one, right? Not including the negative sign. So it should be 5t to the 5th power. And then the leading coefficient is the coefficient in the leading term, which is 5. Alright. So now let's do the last example. H of p, I have 6p minus p to the 3rd power minus 2. So what's the degree? So the degree of the polynomial is 3, because that's the highest power you got. So the leading term is what? The term that containing the highest power, which is this one, including the negative sign. Should be negative p to the 3rd. So what is the leading coefficient? So the leading coefficient should be negative 1, because negative p means negative 1 times p to the 3rd power. Okay, so now let me ask you one question. What about this thing called negative 2? It's a term without the variable. This is called constant term. That means no matter what the variable change, this 2 is always remain the 2. So it's not going to change, so that's why we call it constant term. So for any polynomial, the long-run behavior of the polynomial will match the long-run behavior of the leading term. I'm going to write that down. For any polynomial, the long-run behavior of the polynomial will match the long-run behavior of the leading term. Now let's take a look. So if I give you a polynomial like the previous 3 example that we have in here, what will be the long-run behavior look like? I'm going to rewrite these 3 polynomial. So I have fx equals to 3 plus 2x squared minus 4x to the cube, and then g of t equals to 5t to the 5th minus 2t plus 7t, hp equals to 6p minus p to the cube minus 2. Okay, so let me highlight the leading term. The leading term is here, here, and here. Okay, so the long-run behavior is going to match this power function. Alright, so remember, when it comes to power function, if they're odd number, the function is not like this one, right? If the power is odd. If the power is an even number, the function is going to look like this one. But however, there's a trick in here. We haven't considered the coefficient. If the number is a positive number, they're going to look like this one, no problem. But what if they're negative? Well, let's take a look. What does a negative number look like? For this same graph, if I put a negative, they're going to be what? What happened to them? They are mirrored over the x-axis, right? They just flip it upside down. So now let's take a look again for the even number. If I have yx squared, y equals to s to the 8th, even number. The power is even number. S to the 14th, they're all even number. So now if I put a negative sign in it, what happened to the function? They just flip it upside down, right? So to summarize these, if the power function is a positive number, this is what do they look like. The coefficient, if it's a positive. But if the coefficient is a negative, they're going to mirror it over x-axis. They're going to look like this one. If it's a negative and then even power, the function look like this one. Okay, I am going to call these 1, 2, 3, 4. Alright, so now let's go back to take a look at our first function. Fx equals to 3 plus 2x squared minus 4s to the cube. So the long-run behavior about this polynomial is going to match the leading term, which is negative 4s to the cube. So what does that look like? So it's a negative, we know that it's going to be in the bottom ones, and then since it's to the cube, is a odd number, so the function should match the third graph in here. So that means the long run behavior is going to be as x goes to the right, the function goes down, right? So that means as s goes to infinity, y goes to negative infinity. As s goes to the left, which is negative infinity, the function goes up, which is a positive infinity. So this is the long run behavior of the first function. Okay, so what about the second function? So the second function, gt equals to 5t to the fifth minus 2t to the third plus 17. So the leading term is 5 times t to the fifth. It's a positive number and is a odd power. So that means the function is going to match the first graph. As s goes to the right, which is positive infinity, the function goes up. So goes up means positive infinity. If the function goes to the left, which is negative infinity, the function goes down. So that gives you a negative infinity. Okay, the last one, I am going to change the last one a little bit. Instead of to the third power, because we already done the odd one, I'm going to change that to the fourth power. So, blue pen. So, the leading term for this function is negative p to the fourth. So, since it's negative, we know that it's going to flip. And to the fourth power, odd number is going to look like a parabola, but it's facing down. A facing down parabola, that means as s goes to a positive to the right, to the positive infinity, the function goes down. That means y goes to also negative infinity. So as s goes to the negative infinity, goes to the left, y also goes down. Goes down is negative infinity. So these are the long run behavior of a function. Okay, so after we talked about the long run behavior, now let's talk about a short run behavior. So what is a short run behavior of a function? Well, that is intercepts. So we know that we have two axes, y-axis and the s-axis. Intercept is when the graph intersects with the axis. So that means we have a vertical intercept and the horizontal intercept. So horizontal intercept also called, they have different names, they're also called the zeros or the roots of the function. Of course, they also call x-intercept and the y-intercept. So let's get back to the graph. On the graph, remember last time when we talked about the quadratic function, what is a vertical intercept? A vertical intercept is when the function intercept with the y-axis. When they intercept with the y-axis, then the function is what? When x equals to 0. But what about the horizontal intercept? Horizontal intercept is when the function intercept with the x-axis. So that means when y equals to 0, we have our horizontal intercept. Okay, so now let me give you an example how to find the x and y intercept. So if I give you a function s to the 6th minus 3x to the 4th plus 2x squared. So how do we find the y-intercept? Y-intercept is when x equals to 0. So I have f of 0 equals to 0 to the 6th power minus 3 times 0 to the 4th power plus 2 times 0 to the 2nd power, which is 0. So that means our y-intercept is 0, 0. For x-intercept, also horizontal intercept all the roots of the function, or if I ask you to find the zeros of the function, we want to let y equals to 0. If y equals to 0, so that means fx equals to y, right? That means fx equals to 0. That means I want to set the function s to the 6th minus s to the 4th plus 2x squared equals to 0. Now, how do we solve for x? Well, the easiest way to do it is to factor them. What do they have in common? They all have x squared. So I factor x squared out, I have s to the 4th minus x squared plus 2. And then I can use AC method to factor whatever inside the parentheses. So I have x squared to factor this part out. So let's do a quick review. What is AC method? Well, AC method is we want two number multiply equals to 2, which is, let's use a times b, multiply equals to positive 2, and then we want the sum of these two numbers equals to negative 3. And then after we find these two numbers, we can write the function into x minus a times s minus b. Oh, sorry, I said that wrong. Should be plus a and b. Okay, so now let's take a look. What two number? A times b equals to 2 and the a plus b equals to negative 3. Well, maybe a equals to negative 1 and b equals to negative 2. Let's check it out. A times b, negative 1 times negative 2 equals to positive 2, and the a plus b, which is negative 1 plus negative 2 equals to negative 3. So that means our function can be factored into s minus 1 times x squared minus 2 equal to 0. So after that, then we break apart to find the solution. Either x squared equals to 0, or x squared minus 1 equals to 0, or x squared minus 2 equals to 0. So I can have the answer x equals to 0, or x equals to positive or negative 1, or x equals to positive or negative 2. So our x-intercept, we totally have 5 x-intercept. Or 5 zeros, whatever you want to say. So I have 0, 0, 1, 0, negative 1, 0, square root of 2, 0, and the negative square root of 0. Okay, let's do a similar example. Another example to finding the vertical and horizontal intercept. So g of t equals to t minus 2 squared 2t plus 3. Well, this is nice. They already give you the factored form. So that means we don't need to factor it. So in our previous example, that they give you a standard form. So your first approach is you try to factor them out. Okay, when you try to solve the x-axis. Okay. We want to find the x-axis or the s-intercepts, zeros or roots. So that means I want the function equals to 0. So I have either t minus 2 equals to 0 or 2t plus 3 equals to 0. When I solve it, I have a t equals to 2 or t equals to negative 3/2. You can calculate that by yourself. Well, we haven't found our y-intercept, which is our vertical intercept. Vertical intercept is we need to plug in x or t, in this case it's t, equal to 0 into the function. So when t equals to 0, we have g of 0 equals to t minus 2 squared times 2 times 0 plus 3. So this is equal to 12. Okay, so now the next thing I want to show you is the multiplicity. So what is multiplicity? Well, if the factor is repeated twice, we call it double zero. We also call the zero have multiplicity of 2, which is when do they repeat? Let me use this one. In here, this is a factor, right? And they have a power 2. That means this power repeated. So we call this one is multiplicity of 2. Multiplicity 2. And for the next one, this one, they didn't repeat. They only have a 1. So that means this is what? Multiplicity of 1. Okay, so let's look back at the earliest example. Does this root repeat? It didn't, because it only have 1 degree. The factor only have 1 degree, so we call this multiplicity of 1, similar to this one. So the root didn't repeat because the parenthesis, the whole factor, doesn't raise to the power. So this one also is a multiplicity of 1. But now take a look at this one. This is what? X squared. You square that. X itself is a factor, and then you square. So that means this has this 0, or this root, or this x-intercept has a multiplicity 2. So what does multiplicity do? Well, multiplicity will affect the short-run behavior of the graph. Remember, these are x-intercept. Well, when you intercept with the x-axis, the graph can be different. You can either be like this one, or they can also be this one. So what's the differences? Or they can even be these ones, like a W. So now let's take a look at the x-intercept. We have two types of x-intercept. This one, the x-intercept cross the x-axis. This one also cross the x-axis. This one is cross x-axis. But what about this one? This x-intercept bounce on the x-axis, the x-axis. That means they touch it and bounce back. This one is what? Cross. This one also cross. Bounce, sorry. And this one also bounce. Okay, so when do they bounce? When do they cross? Well, this one is depending by the multiplicity. If the multiplicity is an odd number, then the graph will crosses the x-axis. If the multiplicity is even, then the graph bounces the x-axis. So now we have all the tools that we need to graph our polynomial. But before then, I would like to show you more example about how does the multiplicity work. Okay, I have fx equals to, I'm going to make up some numbers, x plus 3, s minus 5 to the cube, and then s minus 7, and then s plus 8 to the 6th power. Let's say this. So how many x-intercept this is going to be? Well, they will have 1, 2, 3, 4, because when we factor, we set this equal to 0, we end up to have 4 roots. So where are they? They're going to be at x plus 3 equals to 0. We want to set the equation equal to 0 to find the x-intercept. Then x is equal to negative 3. So we have our 1 in here. And then another one is x minus 5. So another x-intercept is at here equals to 5. And then 7 and negative 8. Okay, so now let's look into their multiplicity. When x equals to negative 3, we have multiplicity of 2, right? Multiplicity, oh, this is hard for me, equals to 2 because the power of 2 in here. And then here we have what? Multiplicity of 5. And then when x equals to 7, we have multiplicity of what? This doesn't have any power. Does it mean 0? No, if it's 0, this whole factor will equal to 1. So this multiplicity is 1. As for the last one, the multiplicity is 6. Okay, so we talked about that if it's even, the function is going to be bounced. If it's even, that means this one is even, equals to 2 is even. So that means at here the graph is going to bounce. So in here, the graph is going to be what? It's an odd number, the multiplicity is odd number. So this is going to be a cross. And this, since it's equal to 1, an odd number, the function is going to be cross. So okay, here is the example how we do the whole graph. So how do we graph this? So now let's take a look. What's the degree of this function? So how many x do we have? Well, we have s to the cube. There's a 2x in the first factor, and then 5x for the factor factor, so totally is 7x, and then 1s for the third factor, so 8x, and then s to the 6th power. So we totally have s to the 14th power. And do they have any coefficient? No. So which means it's not really no, the coefficient we consider 1. So that means the highest power is x to the 14th. So the leading terms is going to be x to the 14th. When you factor this out, you will get the leading term. Okay, so the leading term gives us what? The long run behavior of the polynomial. We talked about that earlier in here, right? Since it's x to the 14th, so that means the long run behavior is going to match which function? This one, right? Positive and even, that means look like a parabola. As s goes to the right, the function goes up. So that means y goes to infinity. As s goes to the left, which is negative infinity, y also goes up. So y goes to negative infinity. So the graph is going to match in the behavior like that. So this is, let me use a blue pen. This is our positive infinity. To the left is negative infinity. To the top is positive infinity. To the bottom is negative infinity. The graph long run behavior, remember it's long run, that means when they go into the infinity, they're going to match. So that means at the end, the graph is going to look like, oops, sorry. At the end, the graph is going to look like this one, going up and up, right? Because they match in the long run behavior. So it's going up. Now we're going to touch our first intercept, x equals to a. It's going to bounce. So we bounce them back. And then how can we go to the second x-intercept? Well, we make a turn. When it goes to the second x-intercept, we bounce again. We haven't found out where's the y-axis. Let's say it's here. Okay, when it comes to these x-intercept, they're going to what? Cross. Right? They told you that its multiplicity is equal to 5, so this is going to cross. And then when it comes to this x-intercept, the last x-intercept, the graph is going to cross it again. So see, after they cross, they're connecting back to the end of the graph. So this is going to be the graph of this polynomial. So let me recap this. So to draw a polynomial, what we need to do is to investigate the long run behavior and the short run behavior. So for long run behavior, it's determined by the leading terms. They have either like this or this, only for possibility, because they're going to match in the long run behavior of the power function. Okay, and then we also have the short run behavior, which is the vertical intercept, which is y-intercept, and the horizontal intercept, which is x-intercept, the roots of the function, and the zeros of the function. Under the horizontal intercept, we also have what? The multiplicity. So multiplicity determined by if the even number is going to be a bounce, if an odd number, the graph is going to be cross. And then all the things we're going to link it together. Okay, now let's have another example. Let's try to do the whole thing again. If I given you a function fx equals to negative 2 times s plus q to the 2 and x minus 5. First thing, what is the long run behavior? Well, long-run behavior determined by the leading coefficient. Let's see what will be the highest power look like. So we have s to the second power here, so we have a 2x, times another x. That gives us s to the third power. And here we have a coefficient, so that means we need to times -2. So the long-run behavior is going to match this power function. -2x to the cube. Well, -2x to the cube means the function is going to look like this way, right? If the function look like this way, that means as x goes to the right, the function goes down. So y goes to -infinity. As s goes to the left, which is -infinity, the graph goes up, which is +infinity. So the next I want to investigate is the short-run behavior. So for short-run behavior, we have y-intercept and x-intercept. To find the y-intercept, we need to substitute x equals to 0 into the function, because when the graph intercept with the vertical axis, the x coordinate equals to 0. So with -2 times 0 plus 3 squared, 0 minus 5. So I have what? 0, 19. This is 19. So that means our y-intercept is 0, 19. Next is our x-intercept. Our s-intercept is the function will factor for you. So we have a 2x-intercept, right? Either s plus 3 squared equals to 0 or s minus 5 equals to 0. We want to set the whole function. Let me not skip this. So to find the x-intercept is we want to set the whole function equals to 0. So to break this apart, since it's vector, we have either s plus 3 squared equals to 0 or s minus 5 equals to 0. So that gives you 2 x-intercept. Either s plus 3 equals to 0 or s equals to 5. Because it's square, so 0 squared equals to 0. So that's why s plus 3 equals to 0. So x is equal to -3. So this is our 2 x-intercept. -3, 0, and the 5, 0. But so short-run behavior, we also need to investigate the multiplicity. So for this x-intercept, since the factor we put twice, double 0, we call it double 0. So that means this multiplicity is what? 2. And for this one, it didn't repeat, right? It just single term. So that means the multiplicity is 1. Let me write the whole things down. Okay. So if it's an even number, the graph at here is going to be a bounce. If it's an odd number, the graph at here is going to be a cross. Okay, so we have everything that we need. Now let's draw the graph. Okay, first thing, we label our intercept. We have what? Y-intercept 19, 0. Let's say here is our 0, 90. And then we also want to have a x-intercept 5, 0 and -3, 0. And we want to label everything that we know. I know that at here the graph is going to be a cross, and at this x-intercept the graph is going to be a bounce. And now we want to know where does the graph start. The graph, when x goes to infinity, y goes to negative infinity. Wow, that means the graph is going to end up in here, but where does it start? I'm sorry, I should do the start first. When x goes to negative infinity, which is to the right, to the left, y goes up. So that means the graph starting here. Okay, now we can connect all of these evidence together. So I'm going to use a green pen. So starting on the upper left, when they goes to meet the first x-intercept, this is going to bounce up, and then we touches cross our y-intercept. And then when it comes to y-intercept, the graph need to make a turn, otherwise they can't go back to the x-intercept, the second x-intercept. At this x-intercept, the graph is going to be crossed. So after you cross it, you're connecting with the end. So the graph is going to look like this. Okay, so here is our graph of polynomial. So that's it for this video. So next time I am going to investigate about how can we find the inequality about a polynomial.